Hello, we're going to talk about population-based healthcare and measures of association. So this PowerPoint should be used with the Gordis textbook, chapters 11 and 12. I have some page numbers on here that can be helpful. Relative risk and odds ratio, they're covered in chapter 11. Attributable risk is covered in chapter 12. So to understand this PowerPoint assumes that you have a fairly strong foundation in research. So if you remember that RA is a remainder of a type 1 error and AR is a reminder of a type 2 error, type 1 errors are so important that researchers set an alpha level designation for how much they're willing to risk, rejecting the null hypothesis when they should have accepted it. So what's meant by association? It's the relationship between a risk factor and an outcome. Is there any association or established relationship between them? For example, is there a relationship between teen pregnancy and depression? So why is this important? We need to identify the risk of an error that occurred in a study design or a process or analysis of study data that interferes with the purity of the study outcome. So it's very important to be able to know how to do statistical analysis of studies so that you can actually identify the relevance or if there was a change. I remember when I did my doctoral project, fortunately, I was able to hire a statistician to do my data. I had collected all the data, she analyzed it, and then we had a conversation. She explained it all to me. And my implementation of change, though small, did have an impact. So my project was on antibiotic stewardship in the urgent care. Now, let's look at bias. Bias sometimes is thought of as somebody messed up, but it doesn't mean that. It doesn't mean that the investigator is prejudiced. If you look at page 197 and 198, sources of bias such as recall bias are discussed in detail. Direction away equals overestimate of the significance of the findings towards an underestimate plus give examples using RRs. Real relative risk is going to be introduced in slide 7. It shows that a small amount of bias change, 2.3 or 2.8, large amount of bias change, 1.0 to 5.0, and bias can arise in all study types. It's important to note that timing in the analysis phase bias can be evaluated, but it can't be fixed. So you must pay attention to it during the design and implementation phases of any project. All right. Now that the outcome of interest has been defined and measured and the data are complete, it's time to analyze that data. So determining whether an outcome is directly caused by a treatment or occurs coincidentally is an age-old problem. So it's been around for ages. It often establishes a causal link, which can be difficult, and causation is assigned to an intervention where the evidence can't prove this. So in other words, the researcher should have reported association, not causation. There are many examples where association may have been mistaken for causation, and it's important that when assessing the evidence of a causative effect, proper trials are conducted to rule out the other variables. Determining which outcome measures should be used to analyze study results. The principal measure of association used in cohort studies is the relative risk. The principal measure of association used in case control or cross-sectional studies is the odds ratio, because no incidence of data is available. If you look in your Gordis book, page 217 to 226, it's going to go into more detail on this information. So formula for risk ratio or relative risk, RR, risk of disease using the incident proportion or attack rate, in a group of primary interest divided by the risk of disease and using the incident, proportion, or attack rate in a comparison group. So I know that it sounds complicated, but if you break it down and do it one step at a time, it makes more sense. Attributable risk will be explained also as we move on in this presentation. Now, if you look on page 218, you're going to see a table. And this, for example, in a study examining the association between hormone replacement therapy and colorectal cancer among women, the RR would be the incidence of colorectal cancer among the women who took HRT divided by the incidence of colorectal cancer amongst women who did not take HRT. So if the relative risk was 1.4, what would be the causal interference in this example? So we're going to look at slide 4 for the examination of language. So you can go back and look at that slide for reference. Create your own to be used with the following information. So let's do this. You don't have to make your own. You can if you want to, but if you're going to do it, you can use some scratch paper and draw a table and fill in all 9 cells. So let's say 400 people were exposed to a risk factor and 600 were not. Of those exposed, 50 became ill with the disease being investigated. Of those who were not exposed, only 15 became cases. Calculate the incident rate for those exposed and for those not exposed to the risk factor, and then calculate the relative risk using the formula that we discussed in slides 7 and 9. So it's really much easier than you think. When you create a table, the positives are always in the upper left cell. So you can use this as an example of what we're seeing here. Let's have a review. Relative risk is a measure of association used for determining a causal interference or the risk of exposure on having a condition. So out of the total number of persons exposed or who exhibited a particular characteristic, A plus B, A represents the number who became actual cases. So out of the total number of persons not exposed or who did not exhibit the characteristics C plus D, C represents the number who actually became cases. Now let's calculate the relative risk. We're going to divide the top incident rate by the bottom incident rate. And look carefully at table 11.6 in the Gordis book and practice interpreting it using the language at the bottom of page 217. And table 11.4 on the same page, it illustrates the concept of relative risk. Now, let's use an example. How is the incidence rate calculated? Now, using the 4-square chart that we had on the previous slide and the numbers you filled in the slide number 8, okay? So out of the total number of persons who were exposed or exhibited some characteristic, A plus B, A represents the number who became cases. The number exposed is 350 who did not have the disease. So the number of unexposed, 585 who did not have the disease. The number of cases among the exposed, 50, therefore 350 were exposed but did not develop the disease. The number of cases among the unexposed equals 15, therefore 585 were not exposed and did not develop the disease. So look at the interpretation at the bottom of this slide. It's very important. Now this one is referring to smoking and bladder cancer, the relative risk. So is there a relation between smoking and bladder cancer? Well, according to this data, bladder cancer is 5 times greater in smokers than non-smokers. So it's associated with 5 times the risk of bladder cancer. So smoking is no good even for bladder cancer. All right, the risk interpretation is discussed in your Gordis book, page 217 on the right column. I want you to look at table 11.4 on page 217. So it goes into depth. We just keep repeating the same thing over and over again so that you'll have a greater understanding of what relative risk is in a cohort study. Odds ratio. Now, page 220 in your Gordis book interprets odd ratio, and it is a measure of association between the frequency of exposure and the frequency of outcomes used in case control or cross-sectional studies. Now, let's think about a case control study. The investigator starts by determining a definition of the case to be investigated. So, if you learned back in research, your PICO question, right? And then subjects are grouped as either those with the case or those without the case. Therefore, no new cases are considered. It's just this group. There's no incidence data to be calculated, so we can't determine relative risk. Relative risk is more commonly used in measure of association. It's not always possible, though, and that will be explained further in slide 20. So, in other words, let's break it down a bit. An odds ratio is looking at the likelihood of an outcome occurring based on the exposure. So it's a different measurement. Now let's look at case control study. Look at your Gordis book, page 222, and know how to calculate a case controlled study. So this table was filled out, and so we are using the example of IV recreational drugs. So here we have 61 people who use IV recreational drugs and they're HIV positive. 312 who are not recreational IV drug users do not have HIV and so forth. So do the math. You'll see it on the next slide. The odds ratio that IV drug use is related to HIV prevalence is AD divided by BC. So we're going to look at the next slide so that you can see the interpretation of this. All right. It's impossible to determine whether IV drug use predisposes HIV positive status. So the correct interpretation of this odds ratio is really vital, and read the interpretation very carefully. The interpretation of this is that odds that an HIV positive person using IV drugs is 9.4 times the odds that an HIV negative person uses IV drugs. So that's I think that's relevant, right? That IV drug use increases the risk. Let's look at this one. Gordis, page 223. The problem that we see with odds ratio is that it's not always going to provide an accurate picture of the risk between a contributing factor and the outcome. So if the prevalence of that outcome in the population is very high, so let's look at the same population of 574 people from slide 14. What if 388 of them were HIV positive and not just 88? Does that change things? So this chart can be helpful determining which outcome measure should be used to analyze study results. Again, the difference is that incidence data is not possible in a cohort, case control, or ecological study since the cases exist at the start of the study. So an ecological study is an observational study used with community or population level data. So confidence intervals are not discussed in the Gordis book, and I use those. And it helps determine. I'm surprised it's not in there, but It's a computed interval of values that with a given probability is to say contain true value of the population parameter. So the range of the confidence interval is used to evaluate the significance of the findings. So I know when I did my presentation or when I did mine, the counter was it had to be, in order to be relevant, it had to be 2 deviations from the norm. So, but then again, this is not a statistics class. This is a population health class. I want you familiar with these things because honestly, if you understand these things, it makes it much easier to read journal articles. It gives you a greater perspective of exactly what they're talking about, what their limitations are, and really the reliability of the study. All right, so let's see. Based on sample statistics, an odds ratio of 5.2 with a confidence interval of 3.2 to 7.2 suggests that there's a 95% probability that the true odds ratio in the population would be likely to lie in the range 3.2 to 7.2, assuming there is no bias or confounding. So sometimes a 99% confidence interval is used instead. So you can be sure that out of every 100 times, in 99 of them, the sample measure of association is the same as your target population. So look at the size of the confidence interval and read point number 2 in the last slide. Attributable risk. This is calculated as the incidence rate in exposed minus the incident rate in non-exposed. So this is used to determine the amount of disease incidence that can be attributed to exposure to a specific factor. It's useful in developing disease prevention. Attributable risk is A divided by A plus B minus C divided by C plus D. It's a measure of risk difference and determines the extent to which risk is related to exposure. In a cohort study, it refers to the difference. Note that subtracted, not divided. Oh, made a boo-boo. Oh yeah, it is subtracted. It is there. I see it. Between the incidence rate of a disease in the exposed group and the incident rate in the non-exposed group. Now let's look at the power and probability level. Power or probability or P level, I always called it P, is defined as the measure of the likelihood of rejecting false hypotheses where something could have occurred by chance. So it's used when there's a normal distribution curve and it allows you to identify the most significant data that is lying in the critical tails. Typically, power increases as the sample size increases. So a p-value of 0.5 is the customary level for statistical significance. So let's talk about what does that mean. So the P level is the probability level. It means the probability that a data point in that region could have occurred by chance. So a probability level of 0.05 means that only 5 out of every 100 times this result could have occurred by chance. That means that less than 5 out of 100 times a false hypothesis was rejected. If the probability level was 0.01, then less than 1 out of 100 times will a false hypothesis be rejected. So with a larger sample size, it's more likely that the false hypothesis will be rejected, as it should be. So power has increased. The level of significance, or alpha, is the area in the critical region. If the p-value, remember that stands for probability level, is less than where the alpha level, the level of significance, was set, then those data points are considered significant because they're unlikely to have occurred just by chance. Now, let's look at identifying significant data using probability levels. I want you to remember the 68, 95, and 99.5 rule. This is for 1, 2, and 3 standard deviations from the mean. And this chart breaks it down into half standard deviations, but gives the same numbers. I want you to look at the narrow region in the tail. That's where the alpha level is set. The alpha level sets how much risk of a type 1 error the researcher will allow. And this is a normal curve. This is a normal bell curve. We use it in statistics all the time. So the level of significance, the number alpha is the threshold value that we measure p-values against. It tells us how extreme observed results must be in order to reject the null hypothesis as a significant test. So let's look at this slide. There's a lot of information on it. The p-value tells what the probability is that the test statistic could have occurred by chance. How extreme was the data point in the sample? If the p-value is greater than alpha, then the result's not statistically significant and could have occurred by chance. Therefore, reject the research hypothesis and keep it null. If the p-value is less than alpha, it is significant, and the null hypothesis should be rejected and the research hypothesis will be supported. So as I said, we used a little bit of different verbiage when I was in my doctorate program. We used standard deviations from the mean. So if my p was 2 standard deviations from the mean, it was considered significant. So this is the same thing, just using some different verbiage. Type 1 errors and their level of significance. So the alpha level is the level of significance. Remember that. It's the likelihood of making a type 1 error. So if the alpha level is set at 0.05, then only 5 out of every 100 times a type 1 error is made, or a false claim of significance. If the alpha level is 0.01, then only 1 time out of 100 a type 1 error is likely to occur. With a type 1 error, you're going to reject the null hypothesis when it should have been accepted. So there's not an evidence of significant findings. So the power level of making that alpha mistake increases with the greater sample size. So you need to be cautious. And again, as I said, this is not a research course. This is a population health course. But you're going to be reading a lot of research data as you are looking up these statistics. And you need to know what they mean. And so that's the essence of this PowerPoint presentation. This is one that you may have to listen to a couple times before it finally sinks in, because this data is, or this information is very deep. So again, that's one of the reasons I'm creating these voiceover PowerPoints, so that you can listen to this a couple of times as needed, so that you can understand the content with a greater understanding.